7th International Physics Olympiad year 1974 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested at fred1996@hotmail.com or use Skype name Eduard F 1996. Problem number 1. A hydrogen atom in the ground state moving with the velocity v collides with another hydrogen atom in the ground state at rest. Using the Bohr model, find the smallest velocity v0 of the atom below which the collision must be elastic. At velocity v0, the collision may be inelastic and the colliding atoms may emit electromagnetic radiation. Estimate the difference of frequencies of the radiation emitted in the direction of the initial velocity of the hydrogen atom and in the opposite direction, the fraction expressed in percent of their arithmetical mean value. You can use next data mentioned here. Solution for the problem number 1. According to the Bohr model, the energy levels of the hydrogen atom are given by the formula En equal negative EI over n squared, where n are quantum numbers 1, 2, 3, etc. The ground state corresponds to n equal 1, while the lowest excited state corresponds to n equal 2. Thus, the smallest energy necessary for excitation of the hydrogen atom is delta E equal E2 minus E1, which is 3 over 4 EI. During the inelastic collision, a part of kinetic energy of the colliding particles is converted into their internal energy. The internal energy of the system of two hydrogen atoms considered in the problem cannot be changed by less than delta E. It means that if the kinetic energy of the colliding atoms with respect to their center of mass is less than delta E, then the collision must be an elastic one. The value V0 can be found by considering the critical case, when the kinetic energy of the colliding atoms is equal to the smallest energy of excitation. With respect to the center of mass, the atoms move in opposite directions with the velocities v0 over 2. Thus, we have 1/2 mh multiplied by 1/2 v0 square plus same 1/2 mh multiplied by 1/2 v0 square must be equal to 3 over 4 EI. And from here we can find that v0 equals square root from 3 EI over mh, which is approximately 6.26 multiplied by 10 power 4 meters per second. Consider the case when v equals v0. The collision may be elastic or inelastic. When the collision is elastic, the atoms remain in their ground states and do not emit radiation. Radiation is possible only when the collision is inelastic. Of course, only the atom excited in the collision can emit the radiation. In principle, the radiation can be emitted in any direction, but according to the text of the problem, we have to consider radiation emitted in the direction of the initial velocity and in the opposite direction only. After the inelastic collision, both atoms are moving in the laboratory system with the same velocities equal to 1/2 V0. Let F denote the frequency of the radiation emitted by the hydrogen atom in the mass center. It means at rest. Because of the Doppler effect in the laboratory system, this frequency is observed as c denoted the velocity of light, f1 equal 1 plus 1/2 v0 over c multiplied by f. For radiation emitted in the direction of the initial velocity of the hydrogen atom, and f2 equal 1 minus 1/2 v0 over c multiplied by f for radiation emitted in opposite direction. The arithmetic mean value of these frequencies equal to f. Thus the required ratio is delta f over f equal f1 minus f2 over f, which is v0 over c. In the above solution, we took into account that v0 much less than speed of light, c. Otherwise, would be necessary to use relativistic formula for the Doppler effect. Also, we neglected the recoil of atoms in the emission process. One should notice that for the visible radiation, or radiation not too far from the visible range, the recoil cannot change significantly the numerical results for the critical velocity v0 and the ratio delta f over f. The recoil is important for high energy quanta, but it is not this case. So that was solution for problem number 1.